Hey folks, welcome to my channel number 10. So we have the problem on our screen. I've directly picked it up from the textbook. So we've been given a set of graphs and the question that we have in front of us is state how continuity is destroyed at x equals x naught for each of the following graphs, right? So I'm going to pull out my draw and let's pick up the first graph that we have, which is this one, right? Which is under figure 9.38, which is what I've highlighted. And let's take a look at this graph. Now, the idea behind this problem is very simple. You will have to understand how to read these graphs and how to examine continuity of these graphs, right? So you see that this particular line, which is this pink line, right, is what the function f of x takes when x is lesser than x naught, right? So let's call that out first. And the blue line, the dark blue line is what we have when x is greater than x naught, right? So now we see that there are two dots, right? One is a dark one, which is, I'm going to circle this here, and the other is a open one. We call it an open circle, which is the one I'm highlighting it out here, right? And we will have to understand what do these dots mean, right? The shaded dot, which is, let me call it 1, and the open dot, let me call it 2. The shaded dot actually means for x equal to x naught, this is your x naught, right? The function takes the value as indicated by the pink line, right? So what do we say? X lesser than or x naught becomes x lesser than or equal to x naught. And the open circle, which is represented by 2, indicates the open circle, basically a dot which is not shaded, right? A point which is not shaded indicates that the blue line, which is after x naught, right, which is greater than x naught for all values, x greater than x naught does not include x naught, right? So that is why we call it as the blue line represented by representing for all x greater than x naught, and the pink line representing all x lesser than x naught, right? So now we see that at x equals x naught, my RHL, which is indicated by the blue line, right, has will have a different value, right? Will have a value which is indicated by, I'm going to call this y1, and by LHL at x naught, I will have to pick up f of x as represented by the pink line, right? Is represented by y2, right? Right. So we can very clearly see that my f of x equal to x naught is y2, and my f of x tending to x naught minus what is the value, which is my LHL, is also y2, right? So this is also my LHL, right? So let's call that out, right? And what is the limit when x tends to x naught plus, which means that x is slightly larger than x naught by h, which is infinitesimal. And for those x tending to x naught, we have our RHL denoted by y1, right? So it's very clear from this graph that LHL not equal to RHL, right? And what does that mean? It means the limit does not exist, and it therefore the continuity gets destroyed at x naught because my LHL not equal to RHL. Still, you know, I have my continuity from the left, right? But this particular function is discontinuous from the right, right? So that's how we will have to uh, interpret this graph and conclude that we do not have a continuity at x equal to x naught, right? So this type of discontinuity is called jump discontinuity, right? So let's call that. So we will move to the next graph, which is on your right, as denoted by figure 9.39. And we have a graph denoted by the pink line where the continuity is destroyed at x equals to x naught because we see this open circle here, right? Which I'm just circling out for you and I'm just calling it 1. It means this particular function is undefined at x naught, right? We will not have to worry about the reasons, but it's undefined at x equals to x naught. And so I do not have an f of x equal to x naught, right? I do not have an f at x equals x naught, right? Whereas when I go ahead and check out my LHL and RHL, so for my LHL will be, you can see that for x tending to x naught minus, right? X tending to x naught minus, and if I calculate the limit of this function, I will arrive at my LHL. And from the graph, I can very clearly make out that as x tends to x naught plus, right, which is very close to x naught but greater than x naught, I can calculate my RHL, right? Right. So at the point x naught, this function is undefined, but in the neighborhood of x naught, I have this function very well defined and they will have finite limits. And this graph, it very clearly indicates that my LHL and RHL are equal, right? Because you look at this, I have my point x naught, but on either side I have my LHL and RHL. And as these points get very close to each other on either side of x naught, they will tend to have the same limit, right? Because unlike the previous graph, we don't see a jump, right? We see a break, but we see a break at x equals to x naught, but we don't see a jump as we move from x naught minus to x naught plus, right? So in this case, we know that this function is undefined at x equals to x naught, and that's the only reason why the continuity is destroyed, right? So the limit does exist because your LHL equals RHL, so these two are equal, right? These two are equal, but your x equals x naught does not is not defined for this function, right? So that's the way to read this particular problem. And so this type of continuity, if I'm able to redefine the function, and you know that we have solved some problems in the past, right, where I redefine my function for x equals to x naught, right? Depending upon what is the value of LHL and RHL, which in this case are equal, if I'm able to define what is my f of x at x equals to x naught, then I can remove the discontinuity at this particular point, and I will no longer have this open circle once I redefine the function. So this type of continuity, you can call it as removable discontinuity, right? So we can remove the discontinuity at the point if it is required. So we've seen two graphs. So the first one was a jump discontinuity where we saw that my LHL and RHL do exist, but they are not equal to each other, right? And therefore the limit does not exist. And it is for that reason that this function is discontinuous at x equals x naught. And the other graph on the right is clearly undefined at x equals x naught because of that open circle what we see as indicated in the graph. So though the limits exist, the function is undefined at x equals to x naught. So we're not able to comfortably say f at x equals to x naught is equal to your limit as x tends to x naught, right? So since we are not in a position to confirm that, this function is discontinuous as x equal to x naught. So the point here is both the continuities are different in nature, right? So with this, we will move to the third and the fourth graph of this particular question, which I have them. I'm just moving to the next part of the screen, and let me, yeah. So I'm going to look at figure 9.4, right? And this is again a very interesting graph. So what we see for x lesser than x naught, this is tending to minus infinity, right? And for x greater than x naught, this is tending to plus infinity, right? So here again, you see that the function is undefined at x equals to x naught, and moreover the limits also don't exist, right? So the limit, it is a limitless function. My LHL is also tending to minus infinity, my RHL is tending to plus infinity, and therefore the limits do not exist. The function is limitless, and at the same time it is not defined at x equals to x naught, right? So therefore you have the function being discontinuous. Now can we remove this discontinuity? The answer is no, right? And can we call it a jump discontinuity? No, right? Because in both these cases we see that the limit does not exist. Both the left hand limit and the right hand limit do not exist, and at the same time the function is undefined at x equals x naught, right? So this is neither a jump discontinuity nor a removable discontinuity, and that's the point you'll have to understand, right? So with this we will move to our figure 9.41, which is this graph. So very similar to the first graph that we saw. So here I see that my x lesser than x naught is indicated by the pink line, and this may not include x naught. And why is that? Like we saw in our first graph, you have this open circle here which indicates that the pink line is defined for all values x lesser than x naught and strictly does not include x naught, right? So that is the interpretation of the pink line. And what is the interpretation of the blue line? The blue line starts from x naught, and this dark point, which we can call it as a closed circle, indicates that this particular function is defined for x greater than or equal to x naught. So here my LHL will take a value. Let me call this, say, y1, right? And my RHL will take a value, say, let me call this y2, right? So in this case, my RHL equals f at x equals x naught. And why is that? Because we have the function defined by the blue line, the dark blue line, for all x greater than or equal to x naught. So my RHL equals f at x equals x naught, and it's indicated by the number y2. And my LHL, which is y1, but it's very clear and evident from the graph that is not equal to my RHL, right? So what does that mean? This function has a jump discontinuity, right? Because my LHL is not equal to my RHL. The function exhibits a jump as you move through x naught, and the function is continuous from the right and is discontinuous from the left. And why is it discontinuous from the left? Because my LHL not equal to f at x equals x naught, but my RHL equals f at x equals x naught, right? So this is another example of a jump discontinuity. So I hope you found this problem useful. Please do subscribe to my channel and support. Thank you.